Welcome, guys, to episode 2 of ReliaCast series. Each episode will be covering a reliability engineering topic. If you haven't seen it yet, please check out episode 1 on LinkedIn and YouTube. I'm your host, Chris Wynn-Jones, and with me, I've got Sam Eisenberg. Hello, Sam. Welcome.
Hey, Chris. How are you doing today?
I'm good, thank you. And today's topic, we are going to be covering a question that has been asked. Can I analyse live data if there is no failures?
Well, that's a fun one.
Thought you'd like that one.
So to start, the answer is yes, but you're making some assumptions. Actually, you're potentially making a lot of assumptions, depending on whether or not you've got data that relates back to a similar data set that you actually believe is going to behave similarly enough that you can rely on it. If the answer to that is no, the answer is still kind of yes, but we get much more limited. It's sort of all in how you manage it, but effectively, without any failure, you can at least prove that you are statistically likely to meet a particular reliability target, sort of using the opposite method to how we usually evaluate data. But the big challenge here is that without failure time, it's a lot harder to determine your exact expected time to failure because, well, you've got only a number of suspended runs, meaning you've got data that you have to terminate because you've yet to encounter any failures. So you've got from time start to time of test or time of observation end, and that's it. Which means that any time to failure you're going to expect to be effectively beyond any of the runtimes that you have, and that makes the expectation of an actual reliability value estimation a little bit harder. Because you can't really get a good confidence level for a value that you have no observable data for. So you can start to get an idea of how long you expect to have something run, and how long, or potentially if you're talking about something that's in cold storage and is a single shot device, what the frequency of it successfully launching or operating are after sitting in cold storage. And there's a couple of different methods we can talk about to get to that. But in general, yes, with a whole lot of asterisks depending on what your expectations are.
Okay. Breaking it down just a little bit. I mean, it's 100 miles an hour there, Sam. Thank you.
Sorry.
So you mentioned in that suspensions. So for our newer audience, could you elaborate more on suspensions?
Yeah, absolutely. So from the perspective of general data types, when we're talking about just live data analysis, so you've got your failures, which usually are pretty easily defined in that you put them into the field, you put them on test. These are your standard pieces of data that you've got a beginning and an end time for. In other words, hopefully you know when it went into service or when it went on test, and you know when it failed, or approximately when it failed. In a second here, we'll probably talk about the notion that even though we're about to talk about exact times, we're also going to talk about the fact that we tend to round exact times to nearest whole numbers in a lot of scenarios. But for a standard data point where we've got an actual beginning and end point, those are complete data points. Where we have, in the case of,
does it matter how many of those data points we have? Is there a minimum or a maximum?
It depends on how you're evaluating them and what distribution you're attempting to use. In general, more is better, although there's definitely a point where more turns into noise, not necessarily required to get a reasonable estimation out of them. Relatively speaking, there's no good estimate. The best advice that I can give is as many as counting will let you have if you're talking about something that's on test, or in the case of something where it's, so let's say for the sake of argument, a multi-dozen million euro defense jet where you have one. You might have to get creative with how you do your testing.
Right.
And you may have a number of repairs between each run, depending on how you're doing things. But
so would you approach something like that by breaking it down into bite-sized chunks? More of the
absolutely.
systems rather than the overall platform.
Yeah, you'd be doing subsystems and below to start, building up to major subsystems, and then system level testing at the end once you've got a good idea what your reliability values are for your lower level systems. We've worked with some companies around that because often they don't have a number of those things that they can put on test.
So say I've got an amount of suspension data that focuses on a single unit on my platform or vehicle, or whatever asset it is I'm thinking about. Whoever you are in the world as a reliability engineer, you have an asset of some sort of your interest. And say you have suspension data, so you have no failure data, hence the question originally. And from that, let's talk about confidence level. How much confidence can I have in the answer that I create or that I predict with that suspension data?
So effectively, the level of confidence you have in this is more or less tied directly to the amount of data that you have. There's definitively a correlation between those two values in all cases, but more so in the case of having no failures. And part of this is that as your data set grows without failures, you can start to gain more confidence that those first couple of tests weren't flukes, and that this wasn't a golden sample, but instead is representative of what it is that you're looking to put under test. And so along those lines, it's the more zero failure samples you have, the greater your confidence can grow that the experiences under test, meaning whatever stresses you're under, whether this is under standard use or under some sort of accelerated use, a similar product that's produced using the same assumptions and same methods will survive, presumably as long as or potentially longer than what your scenario is for testing, which hopefully matches what your expected life is going to be.
Yeah, it's great. And where the question came from, it expands into quite a little bit that I left out of the question. Really was no or few failures, and I thought it was a very interesting point to hold back on, because I think as soon as you do get a failure, I think it's really important that you don't dismiss it. As reliability engineers, we are thriving for that failure data, and to know that people have dismissed it and hidden it and parked it away as we've resolved it, let's ignore it and continue with our good data. And a failure is still good data. I just want to elaborate on that, Sam. Please fire away.
Yeah, no. So, so there's one caveat to this, and it's the one that I think probably anyone that's listening to this is probably already aware of. That, while we're looking to celebrate failures in terms of their statistical value with regard to this, we need to make sure that it is a relevant failure to the actual scenario we're talking about. Often you'll end up with a failure mode that doesn't actually match this, and this is where we end up with varied end times for our suspensions, which actually lets me bring the conversation back around to suspensions. So yes, we absolutely want failures that are meaningful to what we're expecting to observe during the test or in the field. But that also means that if we have a failure that occurs due to the test itself as opposed to something else, that's often we have to time terminate that and use it as a suspension instead of a failure, just as a sort of side note to that. However, the moment we get a failure that is relevant to the test or relevant to our expected failure modes for a field of test, we can start to get suddenly a lot closer to actually getting better data out of this from a life data analysis or a statistical perspective. because suddenly we actually have at least one complete data set in our sample. And this allows us to start to get some values around this. From the perspective of life data analysis, the more failures you have, in other words, the more units you have that have completed an entire useful life from their time to field to end of service, or when they effectively fail out of the test, the more of those we have, we can start to get a lot more confident with this, and with the bounds that come with what we're doing with. And sort of to come back to what I first said, the biggest piece is that this means that instead of sort of trying to guess that, okay, we've got this nebulous bound that we're making a reasonable estimate with and trying to be pessimistic, it means that we actually start to have some data points that we can put within those bounds that say, here's an anchor for where these bounds start and where they end. And so starting to have that really gets important, because it means that we can start to talk about where our relative mean time to failure is going to start, and that gets to be really important.
Final question is about failure mode and mixed failure modes. I mean, is it a problem having data from mixed failure modes, or is it worth spending the effort separating those failure modes out?
So honestly, that depends. It depends on a few factors. I'll keep circling back to earlier things I've said because they're pertinent. When you've got mixed failure modes or different failure modes that are bringing about the end of observation for any of the components that you're observing, there are some questions you need to ask. One is, are you actually trying to separate these out based on different failure modes, or are all the different failure modes that you're observing effectively real failure modes that you're going to consider? And so those would be, are we considering or are we not considering manufacturing defects? Are we considering or not considering user error? So those are sort of two of the most common ones that get debated as to whether or not to leave them out. But if what we're concerned about from the first go is just what is the overall expected reliability of this unit when it's fielded, and we know that there's 7, 12, 50 ways that this thing could potentially fail. And, this is where in some cases the definition of failure really does need to be established beforehand, so that you actually have a good measuring stick to say, yes, that one counts, yes, that one counts, no, that one doesn't, so that you can actually just apply that. So you've got your data. But some tests aren't set up that way. Some tests are set up so that they are looking for a single expected type of failure, that we're trying to overstress something into a particular, failure mode. So, we're just looking for instance, fatigue damage, where we're causing something to flex and bend, and, we're waiting until something breaks, where when we get a failure mode that is unrelated to fatigue whatsoever, that might not be a valid data point for a test where all we're looking for is fatigue. And so there's the case where some of these would have to then be put into the suspension pile, where we yet again have more data without a defined endpoint. Instead of having the time to failure, we have a time to suspension, and we still don't have a good sense on what that overall failure rate might look like for the failure mode that we're chasing. And so it's basically the answer is it depends.
Right. Yes. Yeah. Thank you. Yeah, it's well answered. Yes. Thank you, Sam. Yeah. So I was thinking back to work I've done in the past with life data. In some cases, my failure becomes a suspension with a different failure mode. And it's just it's mixing that around, and it's switching things on and off where they matter and where they don't. But the data's still applicable for another failure mode. That particular failure mode didn't happen for this scenario, so that data is still a suspension data. It's still valid data. We can still use it. So, it's just getting that fine balance between knowledge of which bit of data matters and which bit of data doesn't, but not forgetting it and using it as a suspension. So, just simplifying things vastly, but not losing the valuable data to make that confident calculation. But yes, and once
that's exactly it.
Yeah, exactly. So once elaborating on my previous question about confidence bounds and confidence in data, once we have failure data, we have now got opportunities to bring in confidence bounds. I mean, do you want to expand on confidence bounds now?
Yeah, so the general notion here is that it's hard to have confidence around a center point, or in this case, what we expect our mean value to be, if we don't know where we expect that mean value to be. And so, once we've got a point of data, we can start to say, okay, well, this is at least our expected mean value for this, and suddenly, from a maths and statistics point, this becomes a very focal point for the rest of our calculations. Once we have failures, because once we have more failures, if we start to get failure number 2 and failure number 3, we can start to evaluate the distance and the ranking order of where these are, which means that we can start to apply a lot more statistics to them. And the more failures we have, because the confidence bounds might start out somewhere out here, and as we start to get groupings of failures that aren't randomly distributed across the entire spectrum of all of our testing time, as long as our failures are starting to group into a relative area, that area where we're starting to see the failures is where our confidence bounds are going to start to tighten into, because it's where we start to have a much better sense of, do we have data for it? And so, while some of this sounds like it's fairly common sense, a lot of the actual equations that we're using to get the statistical results are based off of this notion of, as soon as we have a data point or a set of data points to focus on, we can start to really focus in those confidence bounds to determine what it is that we're looking at from a range. And that range is going to be determined based off of, 1, the number of failure points that we have, meaning the more failure points we have, the tighter we can get from a confidence bound perspective, and 2, the ratio of how many failures we have to what the total data set is. Because that's still a factor. If we have four failures but 1 million suspensions, we're still not going to be 100% sure that all of the failures are going to occur within that spread of where those 4 failures occurred. We'll feel pretty good that the next 1 million samples of this are likely to behave similarly, but we're still not going to have a lot of confidence in when those failures are going to occur. We're going to have a little bit wider bounds in terms of the confidence levels we have. But this is a case where, again, more data from a statistical perspective is always going to be better.
Yeah, thank you, Sam. Yes, so that's concludes the topic for today. So that's all from Sam and I. Thank you for watching. We'll see you all at the next ReliaCast. And if you like the topic, then do comment in the comments below. If you've got any ideas for other topics that you would like us to cover, we will absolutely take those on board and include those. And don't forget, it's the usual thumbs up, like, share, subscribe, the usual lingo for LinkedIn and YouTube viewers. So thank you guys, and goodbye for now.